In this video, we study the Schrödinger's equation and its consequences to the quantum mechanics theory. From the classical physics, we know that in order to describe a system, we need to solve either the equation of motion or the wave equation. In the case of the former, the solution has this form. Actually, it can be demonstrated that this solution is simply a traveling wave in the x direction and frequency omega. This solution describes completely the wave and the behavior of the system. On the other hand, in quantum mechanics, we have the wave function to describe the quantum system. Actually, all the information of the system is contained in this function. Also, according to the Born interpretation, the probability of finding a quantum system in a specific state is simply the magnitude square of the wave function. Up to this point, we have seen in previous videos how to normalize a wave function. However, we did not mention how to obtain such a wave function and what properties it has to accomplish. Actually, the way to find the wave functions is by solving the so-called Schrödinger's equation. The Schrödinger's equation is one of the fundamental pieces of the quantum theory. As its name states, it was proposed by Erwin Schrödinger in 1926. It was a reaction to the weird proposals of the quantum mechanics. As an interesting note, Schrödinger was convinced that nature cannot behave in a random way. Furthermore, Schrödinger proposed a thought experiment, also known as the Schrödinger's cat, in which he mocked of the quantum theory of his time. The Schrödinger equation has the following form. Notice that we are working in a one-dimensional case. In the case in which the system is three-dimensional, then the partial derivative with respect to space must be replaced by a Laplacian operator. Although it can look quite esoteric, it is simply a different way to describe the energy of a quantum system. Let's focus on the nature of this equation. The first term is simply the kinetic energy of the quantum system. The second term is a potential at which the quantum system is subject to. If the quantum system is free, the potential is simply zero. After describing the two previous terms, it is clear that the term at the right of the equation is simply the total energy of the system, confirming what we mentioned before. Actually, if we see the classical description of the energy of a system, it can be seen the similarities with the Schrödinger equation. Now, let's focus on the solutions that the Schrödinger's equation accepts. In order to simplify our discussion, we can solve the case in which the quantum system is free, meaning the potential is zero. As we saw before, in such a case, the Schrödinger's equation is written in this way. It is clear that this equation accepts solutions of the following form. It is important to notice that the solutions to the Schrödinger's equation represent the wave functions of the quantum system that we are describing. Note that the constant, A, must ensure the normalization of the wave function. Now, notice that the exponential term is the product of two exponential functions, then it can be separated in the following way. One exponential function depending only on the spatial coordinate, while the other one depending on the time. In this sense, we can define two wave functions. one fully dependent on the space and one depending on time, as stated before. Actually, obtaining this kind of solutions is also known as separation of variables, in the differential equation theory. Let's see one more time the separated functions mentioned before. If we focus on the wave function depending on time, we can see that the angular frequency can be expressed in terms of the energy as follows. Also, due to the properties of the exponential function, we see that the derivative with respect to time of this function has the following form. After this analysis, it is clear that the Schrödinger's equation can be written as follows. This equation is called the time-independent Schrödinger's equation. The name is quite clear, as this equation is only dependent on the spatial coordinate. The analysis that we just performed can be generalized for the case in which the potential is not zero, resulting in the following equation. This equation has the energy of the system in an explicit way. We will see in a future video how useful this equation can be in special applications. Next, we need to see what are the conditions for the solutions to the Schrödinger's equation. In particular, the conditions are three. The first condition is that the wave function must be continuous. This means that the wave function cannot have voids, at least in a finite interval. The second condition is that the first derivative of the wave function with respect to the spatial coordinate must be continuous, unless the potential tends to infinity. Finally, the wave function must not diverge when x tends to infinity. As a complement of the previous condition. To finish the analysis of the Schrödinger's equation, we discuss the two kinds of quantum systems that usually can be found. These are the confined and free systems. The difference between these systems is the kind of potential at which the quantum system is subject to. When the potential is not zero, the system is called confined. An example of this system is an electron subject to the electrostatic potential in an atom. On the other side, when the potential is zero, we call the system a free system. As an example, we have a free electron. In the next video we will see how the Schrödinger's equation is solved for a confined system, and the consequences of the obtained solutions using this methodology. Stay tuned.